Okay, thank you very much. I want to thank the organizers for the invitation, first of all. Today I'm going to be talking about hydrogen. We have been working on hydrogen for the last, I would say, 10 years or so. Yes. So the goal of our effort has been from the very beginning to develop first principle methods to the point that we can accurately describe materials at high density. How do I scroll? Click. Oh, I see. Thank you. So from the very beginning, like I said, the goal has been to develop first principle methods to the point where we can describe hydrogen, specifically hydrogen helium at high pressure. Of course, we started relying on density functional theory, and over the last 10 years or so, there has been a big improvement over the predictive capabilities in terms of what we can calculate and what type of accuracies we can achieve. Eventually, density functional theory runs out of steam, so we need to go beyond DFT levels of accuracy, which is what we have been doing for the last 3 or 4 years or so using Monte Carlo method. So hopefully, I'll very briefly overview the work that we have done over the last 2 years or so, and roughly where we think we are in the understanding of hydrogen at this point. So all the theoretical work is based on the Born-Oppenheimer approximation, which is the highest approximation that we do. In this case, it decouples electrons and ions, and the entire problem becomes completely captured on how you solve the electronic structure problem. Of course, like I said, density functional theory is the workhorse where pretty much every calculation is done, but we're starting to consider seriously the use of quantum Monte Carlo because density functional theory has some very clear problems. This is a schematic diagram of the phase diagram of high pressure hydrogen, where we have, of course, molecular phases at low pressure. As you increase pressure, you eventually become atomic. Liquid above roughly 1,000 Kelvin, and you have ordered molecular phases here, and eventually you have an atomic solid that hasn't been observed, of course. Two of the most important problems in this phase diagram is that the liquid-liquid transition, whether it happens sharply as a first-order transition or whether it is just a smooth crossover, and what happens in the solid as you compress it. So we have done a considerable amount of work on the liquid phase. We found and characterized the liquid-liquid phase transition that happens at temperatures below 2,000 Kelvin. This work was done a few years ago. We see two very clear, whenever we go across a constant temperature, we see a very clear a very clear signature of the transition where we see discontinuities. For example, this is a plateau on the pressure, which would imply peaks in the compressibility, and we see from one end with a clear molecular state with no conductivity. As we go across and the volume changes something like 2%, we end up with a state where now the conductivity is finite and very close to something like 2,000 inverse ohm centimeters, which would be kind of like a poor metal. And we also see now a drastic change in the structure of the liquid, where now it's much more atomic-like. The conductivity, of course, related to the delocalization of electrons. We see a discontinuous change in the conductivity, where on this side of the phase diagram we get 0 conductivity and then suddenly a sharp increase. As we go across 2,000 Kelvin or so, the transition now becomes smooth, and we just go through a smooth crossover. So the transition is effectively first order below a certain temperature. The first time we did this with PBE and with quantum Monte Carlo, with and without 0-point nuclear vibrations to understand. Basically, we wanted to understand what whether any effect would make the transition go away, and in practice it doesn't. It is very robust to pretty much anything we do. But there is qualitatively, all the theories that we have applied so far agree, as long as we do ab initio, namely whether quantum Monte Carlo or very different flavors of density functional theory. But where exactly the transition ends is very sensitive to the actual details of the calculation. On the right, for example, I'm trying to show this is along the principal Hugono, which goes somewhere along this line. I show reflectivity, which is the thing that it's measured with the highest accuracy, I would say, from anything beyond pressure from the experiment. And so the black dots are, for example, the measurements. And I can give you references. I apologize for not putting them up here. And then we have calculations using, there are two things that we're trying to understand here. One is the limitations of the standard DFT functional that's used, which is PBE. Clearly PBE, which I apologize, you can barely see, but it's on green up here, drastically overestimates the value of the reflectivity. Molecules dissociate very early in temperature, and the reflectivity and the conductivity are completely wrong when you do something like PV. Of course, if you go beyond PV and you try to do non-local correlation, then you get results that are very close to experiment. And the difference between blue and red is just exactly how you do the optical calculation, whether you use a hybrid or not. So the influence of doing the proper optical calculation is much smaller than what you actually use to describe the liquid in itself. The other thing that's important is you can see that we have varying predictions on where exactly the liquid-liquid transition happens. I don't have time to go into the details, but basically we have kind of a bracket. The black is roughly the function that gives us the highest transition pressure, and the green is from the credible ones, the one that gives us the lower one. So in practice, the real liquid-liquid transition is somewhere in here. We have now redone our Monte Carlo calculations, and we should have a paper soon where we cover all possible predictions between density functional theory and Monte Carlo, and the final prediction is roughly halfway between these two bounds. In terms of the solid, which is the other area of hydrogen where we have spent a lot of time and there's a lot of interest from people in the experimental community, we don't really know. There have been a lot of effort in the last 3 or 4 years trying to understand the phase diagram of hydrogen on this low temperature, high pressure regime, exactly when molecules, when and where and how they dissociate and metallize also at the same time. So of course, part of this effort led to the discovery of phase 4, which was discovered recently by several groups. I guess I don't want to go into details. On the theoretical side, of course, it's a bit of a mess. It's really, whatever you get is really dependent to exactly what electronic structure you're using. So the other thing that's important is that quantum effects dominate. Hydrogen is extremely light, so of course nuclear vibrations are very large, extremely anharmonic. You have to do a path integral, a quantum description of the ion to begin with. You have to do quantum mechanics for both electrons and ions, otherwise what you get is kind of irrelevant. So to show this on the left, I do calculations with and without 0-point effects, and you can see that there is very little relation between the structure classically and quantum mechanically. So quantum vibrations eliminate all the structuring that you see classically. And in the other hand, I see results comparing quantum calculations with different functionals, and you can see that the degree of dissociation is very sensitive to exactly what functional you're using. The optical properties are also extremely dependent on exactly what you're doing. So on the left, for example, I'm showing in red calculations where you just take a static lattice, you optimize the positions of the ions, and you calculate the band gap, for example. And you can see that if you do that, and this is the experiment on this side, you can see that PVE would give you band gaps that are roughly right if you do proper calculations, for example, GW of the band gap. But then if you include thermal effects, you just do molecular dynamics at 200 Kelvin, for example, you get a huge reduction in the band gap. If you actually do path integral calculations, you effectively close the band gap below 250, which would be completely wrong according to experiments. Of course, experiments have been able to go all the way to roughly 360 and still see a finite band gap. Even if we do hybrid calculations, this still doesn't fix the problem. We have to go to non-local correlation, and we get something that qualitatively now matches experiment. But of course, there are many ways of doing this. I don't want to claim that this is the final step. I'm just saying that there is a very significant sensitivity to exactly what you're doing, and the importance of putting both thermal and quantum vibrations in the calculation is extremely important, since it actually dominates. It's a dominant energy scale. Any static lattice calculation is just going to be completely wrong if you get it on spot on top of experiment to begin with. So DFT, we have been doing a lot of work in the last year and a half or so trying to benchmark density functional theory. We have done quantum Monte Carlo calculations over hundreds and hundreds of configurations, and then we compare that against a plethora, many density functional theories available to us, trying to understand what the limitations are. And basically, the result that we get is that DFT is really, there's no functional that's good enough, really. If you want full predictive capability, you have to go ahead and do a Monte Carlo calculation. I see that I'm running out of time, so I don't have a lot of time to go to the details. If you look on the left, very quickly, this is a measure of how well DFT is doing relative energy differences between different structures, and it's really not good enough. There's no clear winner in this case. If you look now, instead of local energetics, and what I mean by that is if you just do displacements away from local equilibrium, you're just measuring basically something like a phonon or something like a molecular vibration, then you have some clear you can differentiate among them. But of course, in terms of relative energies, everything is pretty bad. What this means now is that there are two functionals that are clearly going to be preferred whenever we want to do any perturbative calculation, like a vibrational calculation, for example, for zero-point energy. If we now go ahead and calculate the relative energy of the candidate structures for the different phases as a function of pressure, we can see, and again, I don't have a lot of time, so we can talk about it after the talk, but there's no functional at the end of the day that reasonably describes what QMC is seeing. We see, so in blue and in purple, we have the atomic phases on this side. Everything else, the other three are the three leading candidates for the molecular side, yes. And we have C2C, which is what's considered the leading candidate for phase 3, coming in and eventually meeting CMCA12 and eventually eventually going into the atomic side. So this is for static lattice calculation, I should say. As I mentioned before, vibrational energy dominates the landscape, really, so any calculation without a very careful introduction of vibrational energy is going to be meaningless. So the problem, of course, is that QMC at this point is a little bit too expensive to do the full phonon calculation. We are actually doing it right now, but what we have done so far is to try to get vibrational information from the FT. And since we saw before that there are some functionals that clearly behave better than others in terms of vibrational properties, we hope that we can get something that's qualitatively correct. If you just go ahead and use a bunch of functionals to calculate vibrational properties and compare predictions among them, you see that there's a very big discrepancy. So this is the mean average, like the root mean square difference between vibrational energies as a function of different structures. And you can see that while on the atomic side, as expected, they all kind of behave the same, and the variance between the different functionals is very small. On the molecular side, it's extremely large. So you get pretty much any result that you want. And I can say this with confidence. If you give me a pressure, I can give you a functional that's going to be very close to that pressure. You can pretty much get anything you want. So the only way of making quantitative predictions, of course, is to try to understand what's the cause of this discrepancy and try to then use the prediction that best ascribes to reality. So we started looking at the energy and all the vibrational properties as a function of the bond length, and it's very clear that the low frequency part of the vibrations are all very well described by pretty much all the DFTs. The big problem is how you do the intramolecular vibration, the H2 vibration, basically. We started looking at the energy as a function of bond length and how well each functional describes the bond, basically the molecular bond, and we came to the conclusion that most functionals, basically that you can make a direct connection between what 0-point energy you get and exactly how far off from reality your bond is. So there is a very perfect correlation between vibrational energy and bond length, and there is the particular functional, which is the one that has been the best so far in everything that we have looked at, that matches the bond length pretty well. So we believe is certainly the leading candidate for doing any quantitative prediction with DFT in hydrogen. So what we do is we combine the energetics that we get from Monte Carlo, the vibrational properties that we get from this particular functional, and then this is the phase diagram that we get for low density, for low temperature hydrogen, where we have the C2C phase, eventually the atomic side on this, the atomic phase on this side, and so the transition pressure is coming out roughly at 447, which by the way is extremely close to this experimental extrapolation of Lubert, which is something like 450. I didn't get a chance to go into detail, but of course, if you do DFT, the typical functional that almost universally gets used, PV, gives you a metal already at something like 250 GPa. If I use the DF2, which is a functional that has been doing very well for the liquid phase, you actually get transition pressures already above 750 or so. So anywhere between 250 and 750, I can tune a functional to give you an answer. So by this I mean that you have to be extremely careful in all the details and exactly what you're doing when you claim predictions, and certainly just straight up using the FT, if you don't really have a way of benchmarking or understanding what the limitations are, it's almost certainly going to give you a wrong prediction. So qualitatively, the FT is doing very well. They all show qualitatively the same picture, but if you want to compare against experiment, you have to be extremely careful. And so I have a bunch of collaborators that I didn't get a chance to acknowledge. They're right there, and I'm running out of time, so I guess I will leave it at that. Yeah.